Okay, first things first. I realized as I was teaching it, man, I was doing a really, really bad job explaining odds ratio, so I'm going to do odds ratio 2.0 today. But other than that, are there any questions on the key terms? So you can save any questions you might have about odds ratio and relative risk. We'll address those. Yeah, Sadie?
Is this lecture recorded?
It is. Yep, it is. Did I hit record?
Yeah.
I thought I did, yeah. Sorry. Today is... Yeah, anyways, today's been an interesting day for me thinking-wise, so we'll see how it goes. Say it.
Population stratification, is that the name of a study or something that you...
No, it's basically the phenomenon in which you have certain alleles that are more common in some populations than they are in another. Okay. And so you can think of it, it's very similar to what we call genetic structuring, but with population stratification, it tends to refer specifically to alleles and markers that correlate with genetic illnesses. But it's essentially genetic structuring, where there are certain alleles that are just more common in some populations than others. And when you can start to see that, even with very little reproductive isolation, it's very interesting, and it's an indication of very strong genetic structuring. So very strong genetic structuring. Any other questions? All right. Well, that's it. Because I told you in the video, we're going to spend the bulk of our time working through some concepts you've seen before, but dealing with them again, and I think you're going to enjoy them. So we're going to do Hardy-Weinberg equilibrium stuff, but we're going to take it beyond what you tend to do when you only have two alleles. We're going to take it to multiple allele situations, and then we're going to start to ask questions of like which loci do we anticipate being under Hardy-Weinberg equilibrium and why? We'll start applying some of the genetic principles we've learned in this class. And then we're going to talk about linkage disequilibrium in a little bit more detail, and then we'll talk about odds ratios and relative risk. All right? Hardy-Weinberg equilibrium. So some things you've seen before with Hardy-Weinberg equilibrium. P plus Q is equal to 1. And P, of course, is what? Frequency of the dominant allele. And then, so that would make Q, of course, frequency of the recessive allele. And since we know that very few human characters are determined by a very simple dominant recessive relationship, you can probably imagine that we don't often use just this portion of the Hardy-Weinberg equilibrium. This is where you learn it and you get comfortable working between allele frequencies and genotype frequencies, but really we don't stay there very long with human characters. First of all, it's very unusual to find a human character with only two alleles. And even when you do, it's rare to find one where it's that simple, where it's dominant recessive and it's not some co-dominant or incomplete dominant relationship. And really what we've been talking about over the last couple of weeks are, what we have been talking about is the phenomenon of complex diseases. And we know in complex diseases we've got multiple loci with multiple alleles. And so now we've got a lot of really interesting stuff going on. All right. And then something else that you've dealt with before with Hardy-Weinberg equilibrium, P squared plus 2PQ plus Q squared, and that also equals 1. I don't know why I didn't finish that statement, but that is also equal to 1. And then P squared, what is this? Frequency, yes, it is the frequency of dominant alleles squared, which ends up being the frequency of homozygous dominant individuals.
So the first one is the phenotype and this one's the genotype?
No, the first one is just the allele.
Oh.
Yeah, so this is allele frequencies. These end up being genotype frequencies. Yep. Now, if you have a simple dominant recessive relationship, both P squared and 2PQ will have the dominant phenotype. Because 2PQ is the frequency of heterozygous individuals. And again, if it's simple dominant recessive, these heterozygous individuals are going to have the dominant phenotype. And then, so that would make Q squared the frequency of homozygous recessive. Now, these ratios, both the allelic frequencies and the genotype frequencies, are specific to populations. Okay? From one population to the next, you oftentimes have different ratios, and that's this population stratification. That's this genetic structuring, where different populations have different ratios. Okay? And so what this allows us to do is to determine our genotype ratios, what we would predict from our allelic ratios, or our allele frequencies. Okay? Because if our population is in Hardy-Weinberg equilibrium, the proportion of individuals that are homozygous dominant better equal p squared. If it doesn't, then our population is not in Hardy-Weinberg equilibrium. Okay? Or, if our population is in Hardy-Weinberg equilibrium, the frequency of heterozygous individuals better equal 2 times p times q, or again, our population is not in Hardy-Weinberg equilibrium. Because if you only have 2 alleles, your p and your q, I mean, they're pretty much set, right? You count all the number of alleles, you count the number of p's, p divided, or you count all of the alleles, the number of dominant alleles divided by the number of total alleles, that's your p. And that really isn't impacted by anything. I mean, that's your p. But if you take p and you square it, and that does not equal the frequency of homozygous dominant individuals, something's off. Some genotype is either more or less preferred than another for some reason. Could be natural selection, could be sexual selection, could be genetic drift, just random changes. Could be a number of things. Okay, so genetic drift. What you're going to see most often with genetic drift is that you have Q. Let's say for example. I mean, we can make up any number we want, right? It's our class. It's our board. We'll do what we want. Let's say P is equal to 0.95. Okay. Let's just say, for example, P is 0.95. What this is saying is 95% of all alleles are the P allele. 95% of all alleles are the P allele.
Oh, of the P and the Q.
Yes. So P is 0.95, Q would equal what? And this I'm going to force you to do P plus Q equals 1 in your head. 0.05. Thank you. It's Monday, so I didn't want to do the math in my head. But thank you, I'm pretty sure that is right. Okay, so according to this, 5% of all alleles are that recessive allele. So, in your mind, you would say, this is very unlikely that an individual is going to be homozygous recessive. And you're like, how unlikely? Well, if this is conforming to Hardy-Weinberg equilibrium, it should be Q squared. Our frequency of homozygous recessive genotype should be Q squared. Q squared is 0.05 quantity squared, and I know it's Monday, so this might not be right, but I'm pretty sure that this is 0.000, nope, yes, wait, 525, that'd be, yeah, three zeros?
No.
2 zeros?
2 zeros.
Yeah, whatever. I'm okay with this. So this is, and again, it's Monday, so my math might be off, but I believe this is 2.5 people out of every 1,000 are going to be homozygous recessive. Yeah? And you're like, how do you get 2.5 people? I don't know. A child. Or just a gamete. 2 people and 1 gamete. Right? You can't be homozygous recessive. Silly gametes only have one copy of the genome. You're all like, oh yeah, that makes total sense. Doesn't make sense at all. Right? Gametes only have one copy of the genome. They can't be homozygous or heterozygous. They're hemizygous. Okay. So this right here, this is what proportion of your, this is the frequency or the proportion of your population that should be homozygous recessive. But what genetic drift does is some really interesting things. Like genetic drift may from one generation to the next change Q, but within the same generation, it obviously can't change Q. But what genetic drift, if you find a population that's heavily influenced by genetic drift, what you'll find is that a much higher percentage of the population actually ends up being homozygous recessive. That all of your recessive alleles are like present in only a few individuals. And most of your individuals are homozygous dominant. You have very few heterozygous people, and then you have a certain individuals that just are homozygous recessive. And you're like, what happened there? And it's probably founder effect, right? You had a small population come and establish a new area, right? The homozygous dominant individuals, they're making lots of offspring. Those homozygous recessive individuals, they're like, man, we're only mating with other homozygous recessive individuals, and there were many of us, and you just kind of keep this small little subset of the population without a lot of mixing. And so that would be genetic drift, a founder effect, and sexual selection, right? So lots of stuff going on.
Could you give an example that we've seen this happen in?
Well, like with certain genetic illnesses. So certain genetic illnesses, let's go with, I mean, you can choose anything that's where the recessive trait is going to be fairly uncommon. And the recessive trait is what actually determines the genetic illness. So, I don't know, we could go red-green color blindness, and that's not a simple, it's not autosomal recessive, it's sex-linked recessive because it's on the X chromosome. But you can have, yeah, we'll run with this. Anyways, so, you're only going to be colorblind, red-green colorblind, if you have two copies of that recessive allele, or if you're male and you only have one copy because you only get one chance to get it right, because you only have one X chromosome. And so, but let's just talking about in females, and so an example of this would be where you have very few of your total alleles are that mutant allele, but you have a lot of red-green colorblind females. And so you have very few alleles, but they're all present in a group of homozygous recessive individuals. And really you're only going to see that is either in founder effect where people come and establish a new population and not a lot of time has passed, or if you have heavy sexual selection, right? So where people wouldn't mate with a red-green colorblind female. And then so unless they were also red-green colorblind male, and they're like, oh well, like I can't see red and green or distinguish them, so not that big of a deal. Unless, of course, you're in a different country and the lights aren't shaped like they are in your country, and then you're like, which side's the red and which side's the green? Dr. Jones, none of you knew Dr. Jones. Dr. Jones taught here for a long time, and he was red-green colorblind, and he would make fun of people all the time because they weren't red-green colorblind. It was kind of fun. So then we all felt like the mutants. Yeah.
So you're saying, hang on, I was trying to understand. If the whole like different selections and thing in the population, that won't change Q squared, that'll just change Q itself, right?
From one generation to the next, both would be true. Like if you've got something that's influenced by sexual selection or natural selection or drift, it's going to change both Q and Q squared in the next generation.
Right.
But when you're talking about any one specific generation, when you're doing Hardy-Weinberg equilibrium problems, you're dealing in a single generation. Here's your Q. What should Q squared be?
Right.
If Q squared, Q squared is always going to be the same thing, right? If Q and you square Q, I mean, Q squared is always going to be the same thing. Mm-hmm. But if the number of homozygous recessive individuals does not match Q squared,
right,
then you're not in Hardy-Weinberg equilibrium.
And what would cause that?
Again, it would be an evidence that in past generations, you most often it would be caused by genetic drift. Like you had a number of individuals come in, you had kind of a founder effect, and you had an unusually large percentage of homozygous recessive individuals, And then so now if you can maintain that by sexual selection, if homozygous recessive individuals will only mate with homozygous recessive individuals, then you can maintain a small subset of the population that's homozygous recessive, and they're not mixing with homozygous dominant people, so there are no heterozygotes forming. It's also possible to get it under natural selection if your heterozygous genotype is less fit than either homozygous genotype. Now that's less common than what you have with heterozygote advantage, where your heterozygous individuals are more fit than either homozygous individual. So a great example of that, Dana, would be sickle cell trait in areas where malaria is endemic. That your heterozygous individuals have higher fitness than either of the homozygous individuals because they're resistant to malaria. So they have higher fitness than homozygous dominant people that have 2 normal copies of the beta globin gene, and then they're obviously more fit than people with sickle cell disease.
Would you see the genetic drift also in like the royal families in Europe when they would interbreed with each other?
That would be sexual selection.
Okay.
Yeah, so that would be a better explanation of that. Yeah.
I don't think I'm getting the point. Can you draw out what you're explaining so I can see?
Of what?
Of this. I'm not sure what you mean.
In terms of explaining what factors might contribute to this?
What it is that we're talking about. What the thing that's being contributed to. I mean, I'm not understanding. Is it just when?
So right now it's just like, okay, the allele frequencies are the allele frequencies, right? If you've got a population of 1,000 individuals, you have 2,000 alleles, right? And so the allele frequencies are just what they are. If of those 2,000 alleles, 1,950 of them are the dominant allele, that's just what it is. These over here, this is what you would predict if your population is in Hardy-Weinberg equilibrium, which means that there's no genotype that has a higher fitness than any other. There's no sexual selection. There's random mating. There aren't any really big random changes happening. There aren't significant numbers of new individuals moving in and individuals moving out. Most of your growth is vertically by having offspring. And there aren't any mutations, right? There aren't any new alleles showing up or new copies of the same allele. If it's at Hardy-Weinberg equilibrium, then what you would predict is that p squared, whatever p was, which p is the frequency of the dominant allele, so if you square that frequency, in this case, p is 0.95, 0.95 squared would be, what, 0.92 something, I don't even know.
9025.
9025, so 0.9025, so 90% of your population should be homozygous dominant. But that's oftentimes not what happens. Right? If it's not at Hardy-Weinberg equilibrium, your frequency of your homozygous dominant oftentimes will not match your predicted. These are predicted. Maybe that will help to add this. These are our predicted frequencies of the homozygous dominant individual. Predicted frequency of heterozygous, predicted frequency of homozygous recessive based on our allele frequencies.
That does help.
Yeah. Yep. Okay. So then we have a question. Well, what happens when we have more than 2 alleles? Can we still do this? Can we still do this? And the answer is, of course, yes. And then so it helps to know where we get this second equation from. Yeah, I just added something there, so I'll leave it. I'm going to erase this side. Okay, so we know we have this equation, p plus q is equal to 1. Okay? And then the question is, where do we get this equation here? P squared plus 2pq plus q squared is equal to 1. And you know where we get this? Yeah, John? We square this one. We square this side, and we square this side, and we get this equation here. And we're like, that's so cool. And so if we have more than 2 alleles, we just do that every time. And so let's just say, I don't know, for giggles, that we've got 4 alleles, and we'll call them P, and we'll call them Q, and then we'll call them R, and we'll call them S. We've got 4 alleles now, and we know that P is the proportion or the frequency of the P allele, Q is the frequency of the Q allele, R is the frequency of the R allele, S is the frequency of the S allele, and all of this has to add up to be 1 because that's all we have. We've got 4 alleles, and if we add up the frequency of our 4 alleles, it better equal 1, right? Because that's how it works. And then we're like, well, cool, what would our Hardy-Weinberg equilibrium be when we've got a 4 allele situation? And you're like, oh, it's so simple. You go and you square both sides. And 1 squared, that's still just 1. You see how simple that is? And then it's like, oh, we just square that. It's so simple. Go ahead. I don't really feel like doing it at this time, so I'm not going to. But, I mean, essentially what it's going to be is you have p squared, and then you have plus pq, plus pr, plus ps, plus q squared, and then so on and so on, and you've just got all that stuff, and it'd just be a big old long, sweet equation. But we can do this no matter how many alleles we have, but the reality is that it gets out of hand very quickly. And so we don't do those, we allow computers to do those calculations, we just interpret it. We just interpret it. Because we can still figure out, and why are we still only with binomials here? I guess it's not a binomial, because this is a binomial. Why are we still only, how come we only have 2 letters? Either p squared, or it's pq, or it's pr, or it's ps. We can't have 3 letters together. Yeah, because it's diploid, right? Diploid condition, you've got 2 alleles. You got 2 of the same allele, which should be p squared, or q squared, or r squared, or s squared. Or you could be, heterozygous, but there's several different heterozygous conditions. Okay? And so that's the answer. When we have more than 2 alleles, we take all the alleles, we add them up to 1, and if we square both sides, we can get our Hardy-Weinberg equilibrium no matter how many alleles we have. You're like, why'd you do 4? Why not 3? And then we could have actually done this. Because I wasn't going to do it anyways. Okay? All right. Here's where the questions start to get really interesting. Not what happens when we have more than 2 alleles, because it's like, okay, well, we'll just do the same thing. But which loci would we predict to be at Hardy-Weinberg equilibrium? So we've talked about several different areas of variation in the human genome. And they both boil down to ultimately one of 2 groups. It's either a single nucleotide polymorphism or it's a copy number variation, right? All of our differences, all of the variation among human genomes falls into one of those 2 categories. It's a single nucleotide polymorphism or it's a copy number variation. You're like, well, what about if you actually just have a deletion and you lose a portion of a chromosome? Well, it's a copy number variation, right? Instead of having 2 copies, you have 1. So copy number variations can come in several, iterations, right? You can have multiple copies of the same allele, or you can have multiple versions of a repeat, right? Where you can have, maybe there's one allele with 13 copies of a repeated region, there's another one with 15, those are all copy number variations as well. Now, which of these would we expect to be at Hardy-Weinberg equilibrium? And it's not a single nucleotide polymorphism versus copy number variant situation. It's really like both of these have a chance to be at Hardy-Weinberg equilibrium when something is true. Any thoughts?
What do you think?
So both single nucleotide polymorphisms and copy number variants, a specific locus, has the potential to be at Hardy-Weinberg equilibrium as long as certain things are true. And that would be our assumptions of the Hardy-Weinberg equilibrium. Yeah, Nathan.
Small population.
So we need our assumption is an infinitely large population so that genetic drift is not an issue, right? Yeah, of course. So we assume infinitely large, and it's like, well, what is infinitely large? Because that sounds like it's impossible, and it is. It's like the assumptions of the ideal gas law. They are impossible, and yet most gases behave like ideal gases. It's beautiful. Shows you how robust some of these models are. So, yeah, if our population is infinitely large, if their natural selection is not acting on the locus, if sexual selection is not acting on the locus, if there aren't mutations, like it's not a mutational hotspot, What's?
Of
Oh
individuals.
yeah, we're not having people migrate into or out of the population in a significant number. And so of all of our different areas, single nucleotide polymorphisms, some of these will be at Hardy-Weinberg equilibrium as long as they aren't in a coding region. Anyone that's in a coding region or in a region that may not be coding, it may not code for a gene, but it's actively transcribed. So single nucleotide polymorphisms that aren't in an actively transcribed region of the genome are oftentimes going to be at Hardy-Weinberg equilibrium. Because if they're actively transcribed, even if it's not coding, it's still going to be regulatory. And it's probably going to correlate with some kind of genetic character, which means it gives natural selection an opportunity to act on it. And being that many of our single nucleotide polymorphisms are in actively transcribed areas, very few of our single nucleotide polymorphisms will likely be at Hardy-Weinberg equilibrium. Okay? And then we've got copy number variants. Some of our examples of copy number variations would be, trisomies or monosomies, but those are going to be fairly rare. Most of them are going to be repeats, right? Different numbers of repeats, like microsatellites. And one of the benefits that we talked about with microsatellites is that they are usually not under selective pressure, right? Do you remember talking about that with microsatellites? And when we were talking about the advantages of using microsatellites versus the advantages of using single nucleotide polymorphisms? Microsatellites tend to have a lot more variation, a lot more alleles for them, and they are rarely under selective pressure. And so microsatellites, even though you're like, wait, but microsatellites, aren't they going to be mutational hotspots? Yes, they are. But from one generation to the next, even a mutational hotspot has a very low probability of mutating from one generation to the next. Any individual microsatellite. Now collectively, all of our microsatellites together, which I went and looked it up after our class because I was like, I wouldn't be surprised if there are about 100,000. You know how many there are? It's estimated that there are between 80 and 100,000 microsatellites. You're welcome. And so microsatellites, even though they are going to be mutational hotspots, are almost always going to be under Hardy-Weinberg equilibrium. Because natural selection is not acting on them, and as long as your population is not infinitely large, because that's impossible, but large enough that genetic drift is not playing a huge role, most of your microsatellites will be under Hardy-Weinberg equilibrium. And so really, to sum this up, what loci do you predict to be at Hardy-Weinberg equilibrium? Any loci that are not actively transcribed. Okay? Any loci that are not actively transcribed. And then the last question, well, why wouldn't a locus be at Hardy-Weinberg equilibrium? Yeah, because it's an actively transcribed area, so it gives natural selection a place, a natural selection an opportunity to select against certain alleles. Or to select for certain alleles if you have positive selection. Although most of your selection is going to be negative selection, selecting against certain alleles. Okay, so in this case, usually what we say is that natural selection is a very weak force. And it's very slow. But this is one area when you have a really sensitive model, which the Hardy-Weinberg equilibrium is, it's a very sensitive model, you can detect even weak forces. And so if something is not in Hardy-Weinberg equilibrium, and you're talking about human genetics, it's not like a really reproductively isolated group, because then that's almost always going to be drift or sexual selection. It's almost always the result of natural selection. And since you have a really sensitive model, you can pick up even small differences. Okay? Which just is wonderful, because I know what you're thinking right now. You're like, Dr. Engel, could we do this to find loci that we suspect correlate with a genetic illness? And just to be blindly associating it that there's something associated with this locus? And the answer is yes, absolutely you can. And this is what kind of spurns some of the work to start looking at these loci more closely and finding what genetic illness they actually correlate significantly with. But yeah, if you look at a locus and it is not in Hardy-Weinberg equilibrium, it's almost always going to be because it correlates significantly with a genetic illness. And so natural selection is basically working against it. Okay, any questions about Hardy-Weinberg equilibrium? You love it, right? Yeah. Okay. Linkage disequilibrium. Linkage disequilibrium. So in linkage disequilibrium, two loci are inherited as a single unit. And there it says partially, or at least partially, they might be always inherited as a unit, which this is a question I think you brought up on Friday, John. Was it like about these, will they always be inherited as a unit, or is it sometimes that they're, I don't remember exactly what your question was, but so sometimes we have two loci that are linked, but they're not 100% linked, okay? And we'll see that. So to determine the amount of linkage, or the severity of your linkage disequilibrium, we divide our number of recombinant offspring by the total number of offspring. And you're like, what on earth is a recombinant offspring? And so a recombinant offspring is one that is formed by a gamete that represents independent assortment. So a recombinant offspring is one that is formed by a gamete, at least one of the gametes, allowed for there to be independent assortment between two loci. And so this would be as opposed to our parental offspring, in which they inherited whatever those two loci were as a unit from one of their parents. Now, real quickly, I want to show you where this is done best, and then we'll work an example. So this always is going to work best when we cross a dihybrid individual. So an individual that is heterozygous at both these loci that we suspect might be linked in some way, with an individual that is homozygous recessive for both loci. Okay? Shall we? Yeah, we shall. So here's a female, and she is going to be, let's do this. She is going to be a dihybrid individual. She is heterozygous at two loci that we suspect might be linked. That is, that they're too close together to assort independently. And we're going to cross her with an individual that is homozygous recessive. Okay, we'll start here because this one's simple. This male can only make one type of gamete, the gamete that bears the recessive allele for both. You're like, Dr. Engel, what if there's a mutation in his germline? Could he make a different type of gamete? Sure, but it's too complicated. These are the kinds of things that I think is happening inside your head. I don't really know what's happening inside your head. If you're anything like me, when I sit in a class, there's absolutely nothing happening inside my head. And nothing happening inside your head either, but I don't know how many of you are like me. Where you just stare aimlessly and you're like, I'll listen to the recording later. No? Yes. Okay, this female can make 4 different types of gametes. Right? She can make a gamete that has the dominant A and recessive B. She can make a gamete that has dominant for both. She can make a gamete that has the recessive A, dominant B, and she can make a gamete that is recessive for both. Right? So when we do this cross, we will cross this one male gamete that is recessive for both with this all 4 of the female gamete options. And so when this sperm fertilizes this ovum, you get capital A, capital B, lowercase b. Okay, when this sperm fertilizes this ovum, you get capital A, lowercase b, lowercase b. when this sperm fertilizes this ovum, you get lowercase a, capital B, lowercase b. And when this sperm fertilizes this ovum, you get lowercase a, lowercase b, lowercase b. Okay? And so this is, the reason why this is so nice is because each of these represents a unique phenotype and a unique genotype, right? And the ratios should be 25%, 25%, 25%, 25%, or another way we can say this is 1 to 1 to 1 to 1. That should be both our genotype frequencies and our phenotype frequencies. And so this is why it works so nicely, because if we set this up and these individuals produce 1,000 offspring, we should have a 1 to 1 to 1 to 1 ratio. If the loci are not linked, if they are sorting independently. But what's interesting is sometimes this doesn't happen. Sometimes instead of this, let's say we have 1,000 offspring. And we did this a little bit on Friday, but I want to take it to the next step where you can actually see the math. Let's say we have 1,000 offspring. And so we would predict that we would have 250 of these, 250 of these, 250 of these, 250 of these. Okay? That's what we would expect. But let's say we didn't get that. And instead, what we got is this. 400 of these, 400 of these, and then 100 of these, 100 of these. And I think my math is correct, and that would add up to be 1,000. Okay? And we're like, wow, this is really strange. One, we can use a chi-squared analysis to see if we're confident that this is actual evidence that they're linked and not just a statistical anomaly. But we're not going to do that now. Or we can do this and just say, okay, we can determine, we're like, okay, we're pretty confident that these are linked, but we want to know how much are they linked. What is the severity of the linkage disequilibrium? Well, it tells us that we will calculate this by dividing the number of recombinant offspring by the total number of offspring. So if these two loci are linked, what is more common? That you're going to inherit a chromosome directly from your mom as is, or that a crossing over event is going to mix the information between the two loci? Which one's more common if the two loci are so close together that they're linked? What's more likely? That you're going to inherit the chromosome as is, so like just get your maternal grandfather's chromosome as is, or is it more common that you're going to get a mix of your maternal grandfather and your maternal grandmother's chromosome? What's more likely if they're so close together they're linked?
It's the same.
That you're going to get whatever your mom had and it's going to come as a unit. Which tells us that these two are likely the parental chromosome and these two right here are the recombinant. Does that make sense? Because your recombinant is always going to be lower than expected. Your recombinant frequencies are always going to be lower than expected when your loci are linked. Does that make sense?
Yes.
Okay, cool. So we're like, all right, well, let's calculate this. And it tells us we calculate this by dividing the number of recombinant offspring by the total number of offspring. So we have 200 recombinant offspring, right? 100 plus 100 is 200. So 200 recombinant offspring. And we're going to divide that by the total number of offspring. What's the total number of offspring? 1,000. And so this gives us a value of 0.2. And you're like, cool, what does that actually mean? This gives us a relative distance between the two loci. It is not an absolute distance. The only way this can turn into an absolute distance is if we have a way to compare this ratio to an actual physical distance. That's hard to do. But we can do this as a relative distance. And if the two loci assorted independently, what should this equal? It's not going to be 1, because this is what you would expect based on independent assortment, right? Yes? you'd expect 25% of all of the offspring should have these particular genotypes. So it would be 500 recombinant offspring divided by 1,000 total. Yes? So if they were sorting independently, this number should be 0.5. You're like, what if it's over 0.5? Well, that's got to be a statistical anomaly. Otherwise, or it's an indication that crossing over always happens between two loci. But even then, it wouldn't be more, because that would be very strange. It would be, the only way you can get it to be over 0.5 is by a statistical anomaly. Or, actually that's not true. If your offspring that had the parental combination for some reason had lower fitness. But then you're like, how is that possible if mom had those combinations and she's doing just fine? She produced 1,000 offspring, right? So, I don't know. I'm just going with this here. So if you're over 0.5, it's probably a statistical anomaly. Anything under 0.5 is an indication that they are linked. And the smaller the number, the greater the linkage. Okay? The smaller the number, the greater the linkage. And the smaller the number, the closer the two genes are to each other.
So what's with the, sorry, can you repeat again why you did 200 divided by 1,000?
Yeah, because your recombinant combinations are always going to be less common than expected if the two genes are linked. Because if they're linked, they're really close together, right? We're talking about that they're physically linked, and it's not like an epistatic linkage, right? Where the expression of one is influencing the expression of another. Because we know their genotypes, right? We could go and we could look at their genotypes. So we're talking about an actual physical linkage because they're really close together. In that situation, your recombinant offspring are always going to be less than predicted. Because the genes are close enough together that crossing over isn't always enabling them to assort independently. So that's how we could tell that these two were recombinant. The only other way to know for sure is to know what her chromosomes actually look like. But if these are recombinant offspring, it tells us that the recombinant condition is having a capital A with a lowercase b, right? And a lowercase a with a capital B, that's a recombinant. So then that tells us that her chromosomes basically look like this. Okay? And then so if you knew that from the beginning, then you would know exactly what the recombinant offspring would look like, right? Because if these are the parental chromosomes, this is say from maternal grandmother, this is from maternal grandfather, then you know any offspring that have the capital A and the capital B, that they're parental offspring. And any offspring that have one capital letter and one lowercase are recombinant, that a crossing over event happened in between those two loci. To mix them, shuffle the decks. Right? 2 complete sets of the decks, right? And then you shuffle them together. But then you have to end up with 52 cards at the end, and you have to end up with the right amount of each number. Yeah?
Can you go over again how you know that the lower frequency types are the recombinant?
Because that's what has to happen if they're linked. If they're linked in such a way that they're too close together for crossing over to happen reliably in between the two, it means you're going to have way more offspring inheriting the chromosome as is than offspring that get a crossing over event and create a unique chromosome that didn't exist in mom. Right? Because the only way to get these combinations here is to create a chromosome that doesn't exist in mom. Right? To create a chromosome that has a capital A and the lowercase b. We know we got a lowercase b from dad, but we have a second one. The only place it could have came from was mom, but mom's chromosome would look like this, capital A, capital B. Now the reason I knew this is because I went down here and our recombinant numbers are always going to be lower than predicted. And again, it's because if you're not getting independent assortment, it's a lot more likely you're going to keep what you had to start with in mom than getting something that mom doesn't even have. Right? Mom doesn't have a chromosome with a capital A and a lowercase b. But now some of her offspring do, and they inherited it from her. Right? All of the genetic material they got from dad was recessive for both. Yeah, Mia.
Can you define recombinant offspring one more time?
Yeah, recombinant offspring are offspring that have a genetic combination that was not present in the gametes that fused to form their parents. Okay? Because basically, the gamete mom got from paternal grandmother looked like this, had the dominant allele for both. The gamete that came from maternal grandfather looked like this. And so recombinant offspring have chromosomes that didn't exist in the gametes that fused to form their parent. Nathan, did you have a question?
Yeah, what's the relationship between the number we get and 0.2 and like what kind of distance do we get? What do we get?
Yeah.
Base pair?
Let me show you. Basically, all it is, it's a relative distance that we call a centimorgan. And so the centimorgan, 1 centimorgan is equal to a 1% recombination rate. So this right here is a 20% recombination rate, yes? So this would be 20 centimorgans, the distance between two. But again, your question is, what does that actually mean? We don't know. This is oftentimes left as relative distance. The only way to equate it to absolute distance, the only way to do it to absolute distance is to have some conversion factor between a centimorgan and an actual physical distance in terms of number of bases or maybe in picometers or whatever. So we would need to actually have the genome mapped enough that we know the actual physical distance between two loci, and then we could equate that. But the thing is it's going to vary from one chromosome to another, and it's going to vary from one region of a chromosome to another, how much a centimorgan is worth.
Wait, why?
Because the chromosome is not, it's linear, but that's way too simple to think of what the chromosome actually is, because the chromosome folds over and different regions of it associate together. So you might have two loci that are really far apart on the chromosome, but those two regions of the chromosomes are always associated together. And so they are inherited as a unit oftentimes, even if they're far apart on the chromosome. Yeah.
So 0.2 would be how many
20 centimorgans. 20. Mm-hmm. Yep, 0.2 would be 20 centimorgans. And so again, all it does is it gives us relative genetic distance. Yeah. And you're like, well, what is the value of relative genetic distance? Relative genetic distance allows you to develop a map of the chromosome. The order of genes, the relative location of those genes on the chromosome, so that when you go and sequence it, you know where to look. You're not sequencing an entire chromosome that's 100 million bases long, right? You're sequencing a specific region because you've got this chromosome already mapped. And I go, wow, it's really not that big of a deal. If you could sequence an entire genome for $1,500, why not just do it? What if your sample size is, 20,000 Drosophila individuals? Now that $1,500, it adds up. $1,500 times 20,000 is a lot. Okay, and on that note, we are done. And you will not be equipped to do the quiz. So hold off on the quiz. I mean, you can do it if you want, but there's a question on odds ratio, and we didn't get to odds ratios.